Hey everybody, we are going to work through that one ice table problem that we did start. Friday, I think this is pretty much how far we got from most classes. I'd like to just reiterate a few things before actually getting started. Again, an ice table is used when you are either looking for solving for the KEQ constant, the equilibrium constant, or you're trying to solve for one of these guys or all of those guys at equilibrium. Sometimes mostly you're given an initial, in this case 9.9 molar SO3, or in this case also 0 molar. We have nothing starting at for the SO2 and the O2. Cool. So again, what's going on is that you need to, for your initial values, for all three, just place them into your table. Again, molarity would be your moles over your liters. That's how we got the 9.9 molar for the product. And all I'm going to do for the change now is utilize basically some Le Chatelier principle and also some stoichiometry. So in this case, we have 9.9 molar as the concentration of the products. We have no reactants, okay? So this reaction has to shift left initially to make some reactants, all right, since it's in equilibrium, so there has to be some reactants there, all right? There can't be none at the end. So what we're going to do is the change will be x. So I'm going to do is put, that O2 is going to go up by x, but SO2 is going to go up by 2x because of the 2 there. Again, it's all stoichiometry based. If O2 goes up by an x amount, then SO2 goes up by 2 of that x amount because of the coefficient. Then SO3 is going to go down by minus 2x. All right, because the change will be simply x, but the coefficient matters. In this case, that's whether you're doubling, tripling, or quadrupling, whatever your change is based on your coefficient. So our equilibrium then, here I'm going to put, let's see, for O2, well, it's just 0 plus x, so it's going to be x. Then for this guy, it'll be 0 plus 2x, which is simply 2x. And down here, for the SO3, it's just 9.9 minus 2x. All right, so normally at this point, it looks kind of weird because we don't know KEQ, and we still don't know any of those. So we do know one of them at equilibrium, but we'll get to that in a minute. So we're trying to solve again for two other substances, the SO3 and the O2, and also the KEQ. But you're given an important piece of information up here. 0.3 moles of SO2 are remaining in the flask. So again, it's half a liter. So what we're going to do is at equilibrium, that means that we have 0.6 molar SO2 at equilibrium. Again, 0.3 moles over half a liter. That's how we get that. So if we know SO2 is 0.6 molar at equilibrium, well, that equals 2x. There's our little, there's our equation. So our equation is right there. We know that now 2x equals 0.6. Let's get rid of that. 2x equals 0.6. Okay? So we can solve for 2x. Or at least we can solve for x. X equals 0.3. Again, the whole point of this wasn't to solve for x, it was to solve for the equilibrium constant. But you can see where we're going now. If x equals 0.3, you can simply plug in for x. All right? So again, using an ice table, again, it's not the only way to do these problems, but I do think it is the easiest. We're going to do a couple more. I will post another video of another example of this, but you can definitely see once you solve for your equilibrium concentrations, plug them in up here to your expression, and you will be done. I think the answer for this was 801. Great.